Welcome, curious minds, to the deep dive. Today, we're embarking on a journey, really getting into the fundamental nature of matter. And we're drawing directly from chapter 1 of the, legendary Feynman lectures on physics. The chapter's called Atoms in Motion. So our mission for this deep dive, it's to really unpack the immense power of what Richard Feynman called the atomic hypothesis. You'll discover how this seemingly simple idea about tiny particles, it can explain pretty much everything, from the different states of matter we see every day.
Yeah, solid, liquid, gas.
Exactly. Yeah. To complex chemical reactions, and even, maybe most profoundly, the very essence of life itself.
And what's truly fascinating here, I think, is how one, deceptively simple statement can just unlock so much about the world around us. This isn't just a deep dive into physics, is it? It's really about a foundational idea that underpins, all of science. And Feynman, he just had this incredible knack for distilling incredibly complex knowledge into concepts that are surprisingly accessible. Makes it really resonate,
Absolutely. He makes this really bold claim right at the start of his lectures. He posits that if all scientific knowledge were destroyed.
Wow. Imagine that.
Yeah. And only one sentence could be passed on to future generations, it would be the atomic hypothesis, which is all things are made of atoms. Little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another.
And you can immediately see why he chose that specific sentence, right?
Yeah.
That single statement contains just an enormous amount of information about the world. That is, if you just apply a little bit of imagination and, critical thinking, it's not just describing something.
Yeah.
It's truly a foundational principle for understanding everything we observe. Small scale, large scale, doesn't matter.
And to illustrate this power, Feynman invites us on this thought experiment. It really brings the atomic world to life. Imagine a single drop of water, maybe, say, 1/4 of an inch on the side. Looks smooth, right? Continuous.
Yeah, just water.
But if you could magnify it, say, 2,000 times with a good microscope, that drop would suddenly be 40 feet across. Still looks pretty smooth, though you might see some little football-shaped paramecia swimming about in there.
Okay.
But here's where it gets really interesting. Magnify it another 2,000 times. Now the drop stretches 15 miles across.
Whoa.
And suddenly, it's not smooth anymore. It looks like a teeming crowd, like seeing a stadium full of people from way up high.
Right, you start seeing the lumpiness.
Exactly. And if we magnify it just another 250 times, finally, we start to resolve individual atoms. Now, okay, these are idealized in drawings, often 2D, sharp edges, makes it simple. Black circles for oxygen, white for hydrogen.
The classic H2O model.
Right. Each oxygen with 2 hydrogens tied to it.
Yeah.
But you have to imagine them. They're constantly restless. They're bouncing, turning, twisting around in 3 dimensions.
That internal restlessness.
Yeah.
That's absolutely key.
And these things are just impossibly tiny. We're talking atoms about 1 or 2 angstroms in radius. That's 1 or 2 times 10 to the -8 centimeters?
Minuscule.
So small that, visible light is actually too big to properly bounce off them. That's why you can't see individual atoms with a normal light microscope.
It's where classical physics kind of breaks down, isn't it? You're entering the quantum realm.
Exactly. And here's that analogy he gives, which I love. If an apple were magnified to the size of the Earth, then the atoms in that apple would be roughly the size of the original apple.
Wow. That really puts it in perspective, makes you feel huge and tiny all at once.
Doesn't it?
So these incredibly tiny particles, they have these 2 core behaviors. From that sentence Feynman picked out.
1.
They attract each other when they're a little distance apart. That makes them stick together, basically.
Right. That's why water holds together, keeps its volume, doesn't just float away.
Exactly. But 2, they also repel upon being squeezed into one another. They push back.
So they don't just collapse into each other.
Precisely. And this fundamental push-pull, this attraction and repulsion, it explains so much about the physical world we see.
Okay, let's unpack this a bit more then. If this single sentence about atoms has so much power, how does it actually help us unravel the mysteries of, our everyday world? Let's take something simple, like water. Why does it turn into steam when you heat it? Or freeze into ice when you cool it? It all comes back to those moving atoms, doesn't it?
It does.
And it's fascinating how this seemingly abstract idea, this unrelenting motion, directly translates into something we feel, like the sensation of heat. Could you maybe break down that connection for us?
Yeah, absolutely. That perpetual motion, that constant jiggling and bouncing around, that is what we mean by heat. essentially. So as you increase the temperature of something, you're basically just increasing the speed and the intensity of that atomic or molecular agitation. Think about a gas, like steam. When you boil water, you're adding energy, making those water molecules jiggle faster and faster until, bang, they have enough energy to break free from those attractive forces holding them together in liquid water.
So they fly apart?
They fly apart, yeah. They're largely separated now, bouncing around independently. Feynman uses this great analogy. Imagine a room filled with, say, 100 tennis balls just bouncing off the walls constantly.
Okay, I can picture that. Chaos.
Right. And when those tennis balls hit the walls, they push on them. Each tiny push doesn't do much, but add them all up all over the walls all the time.
Yeah.
You get this average push.
Yeah.
And that average push is what our senses or our instruments perceive as pressure.
Ah, okay. That makes sense. So following that tennis ball image, if we crammed twice as many tennis balls into the same room, that would double the pressure, right? Because twice as many hits on the walls.
Exactly. Double the molecules in the same space, they hit the walls twice as often, pressure doubles. Simple relationship.
And what if we kept the same number of balls but just made them move faster, like heated them up?
Good question. If you increase the temperature, you make the atoms or molecules move faster. So now they hit the walls harder and they hit the walls more often because they're zipping around quicker.
So pressure goes up even more?
Right. Pressure increases. It's a very elegant idea how these microscopic actions scale up to macroscopic effects we can measure. Now, this actually raises an interesting point for you, the listener. We can feel these big effects, like temperature changing, but how is it connected back to those tiny interactions? Well, think about compressing a gas slowly, maybe with a piston in a cylinder.
Okay.
As that piston moves in, the atoms hitting it bounce off a moving surface. It's like hitting a ping pong ball with a paddle that's moving towards the ball.
The ball comes off faster.
Exactly. The atoms pick up speed from colliding with that moving piston. So when you compress the gas slowly, the average speed of the atoms increases.
Meaning that the temperature goes up?
The temperature increases, right. And the reverse is true too. If the gas expands slowly, pushing the piston out, the atoms lose energy bouncing off the receding surface, and the gas cools down.
Okay, that makes sense. Now let's go the other way. What happens if we cool our water drop down?
Right.
The random motion, the jiggling, it steadily decreases.
Less energy in the system.
So the attractive forces between the molecules start to win out more, right? And at very low temperatures for water, 0 degrees Celsius, the molecules lock into place. They form a new, highly ordered pattern. Ice.
A crystal.
Yeah, a crystalline array. It means there's a definite place for every atom, a rigid structure, totally unlike the flowing liquid water. And its beautiful symmetry, like the hexagonal structure typical of ice, that accounts for why snowflakes always have those intricate 6 sides. It's the underlying atomic arrangement showing through.
And here's a really curious detail about water. It's actually kind of weird compared to most substances. Ice shrinks when it melts.
Oh yeah, that's counterintuitive, isn't it? Most things expand when they melt.
They do. But ice has this rather open crystalline structure with like holes or empty spaces in it. When it melts, this structure collapses. And those previously empty holes can now be occupied by the jiggling water molecules. So the liquid water ends up being denser than the solid ice it came from.
Which is why ice floats. Okay, that makes sense now.
Exactly. Most other substances, their atoms just need more room to move around when they become liquid, so they expand.
So even in solids like ice, we need to remember the atoms aren't completely still, are they? They're still vibrating?
Oh, absolutely. They're locked in position, but they're constantly jiggling and vibrating in place within that structure.
And melting happens when these vibrations just get too violent, too energetic.
Precisely. They shake the atoms so much they break free from their fixed places in the crystal lattice, and the structure falls apart and it melts.
And if you keep cooling, keep reducing the temperature, the vibrations get smaller and smaller.
Right, down towards absolute zero.
At absolute zero, there's still a minimum amount of vibration, right? Quantum mechanics says they can't be perfectly still.
Correct. There's a 0-point energy, a minimum quantum jiggle. But it's usually not enough motion to melt a substance, with one really weird exception: helium.
Helium.
Yeah. Even right down at absolute zero, helium stays liquid. It just doesn't freeze unless you apply immense pressure to really squash those atoms together. It's a quantum liquid.
Wow. Okay, so we've seen how this atomic theory explains the different states of matter: solid, liquid, gas. But how do these atomic behaviors explain everyday processes, things happening, like evaporation? Let's start there. What's actually happening at the surface of, say, a puddle when it just seems to vanish into thin air?
Yeah, good example. It's all about energy distribution, really.
Hmm.
In the liquid, water molecules are always jiggling and bumping into each other. From time to time, purely by chance, a molecule right at the surface gets an extra energetic kick from its neighbors, a harder bump than usual. And if that kick gives it enough energy, enough speed, it can actually overcome the attractive forces, pulling it back into the liquid. And it escapes. It flies off into the air as a molecule of water vapor.
So they're constantly escaping from the surface.
They are, but it's a two-way street. Molecules from the water vapor in the air above are also constantly bumping back down into the liquid surface and getting stuck again.
Ah, so there's a balance.
There's a dynamic equilibrium. If you put a lid on a glass of water, eventually the rate of molecules leaving equals the rate of molecules returning, and it looks like nothing's changing.
But if you take the lid off,
Right. And especially if you, say, blow the moist air away from the surface, maybe with a fan.
then fewer molecules are returning from the air.
Exactly. The ones returning gets swept away.
Mm-hmm.
So more are going out than coming back in. Net result, the water evaporates.
And here's the really cool part, the surprising consequence. Something you probably use every day without even thinking about the atoms. The molecules that manage to escape, the ones that get that extra energetic kick, by definition, they have more energy than the average molecule left behind, right?
Yeah, they're the hot ones, so to speak.
So when they leave, they take that extra energy with them, which means the average energy of the molecules remaining in the liquid decreases.
The liquid gets colder.
The liquid gradually cools if it evaporates, which is exactly why you blow on hot soup to cool it down. You're speeding up evaporation.
Amazing, isn't it? The same principle cools your body when you sweat. It even drives things like geysers, all down to these energetic atoms escaping.
It really is incredible how these tiny atomic behaviors explain something so familiar. But okay, atoms aren't just moving apart, they're also interacting, right? What happens when those interactions lead to something dissolving? Like salt vanishing in water?
Ah, dissolving. Good one.
You put a salt crystal in water, stir it up, and poof, it seems to disappear. What's the atomic story there?
Well, first off, salt isn't made of neutral molecules like water is. Common table salt, sodium chloride. It's actually a crystal lattice, a very precise grid.
Of charged particles.
Exactly. Charged particles called ions. You've got sodium atoms that have lost an electron, making them positively charged ions,
Yeah.
F plus, and chlorine atoms that have gained an electron, making them negatively charged ions, Cl.
Yeah.
And it's the strong electrical attraction between these opposite charges, this invisible glue that holds them together rigidly in that crystal structure.
So how does water break that apart?
Well, water molecules, remember, are polar. They have a slightly positive end where the hydrogens are and a slightly negative end where the oxygen is.
Right.
So when you put salt in water, these polar water molecules get in there. The negative oxygen ends are attracted to the positive sodium ions.
And the positive hydrogen ends are attracted to the negative chloride ions.
Precisely. The water molecules effectively surround the ions at the surface of the crystal. They jostle and pull, and through their constant jiggling motion, they manage to jiggle loose individual ions, pulling them away from the crystal lattice and into the water.
So the ions get surrounded by water molecules and float off?
Basically, yeah. They become solvated. And this process is also dynamic, just like evaporation. Ions are constantly leaving the crystal surface to dissolve.
But other dissolved ions are also bumping back into the crystal and reattaching.
Right. And the overall balance between those two rates, dissolving versus crystallizing, determines whether, on the whole, the salt dissolves, or if maybe crystals start to grow back out of the solution.
That's a really crucial distinction you made earlier, that solid salt doesn't have separate, discrete molecules like water does. It's just this big, ordered arrangement of ions held together by electrical forces.
Correct. It's an ionic lattice.
Okay. So now let's talk about maybe the most dramatic atomic interactions, chemical reactions. This is where atoms really change partners, isn't it? Forming entirely new molecules.
Yes, this is where the real action is, chemically speaking.
A classic example Feynman uses is carbon burning in oxygen. How does the atomic hypothesis explain that?
Okay, so oxygen in the air, as we breathe it, normally exists as molecules made of two oxygen atoms strongly stuck together, O2.
Right.
Now, carbon can exist in different forms, like graphite in your pencil lead or diamond. Let's just say we have some carbon atoms. If you get an oxygen molecule, O2, near a carbon atom, C, and you provide enough initial energy, maybe from a spark or a flame, to kind of get things started, break some initial bonds.
Then what happens?
Then the oxygen atoms and the carbon atom can rearrange. They can snap together in a new configuration with, as Feynman puts it, tremendous vengeance and commotion.
Vengeance and commotion, I like that.
It implies a lot of energy release. This rearrangement releases a large amount of kinetic energy. The atoms in the new molecules formed are moving much faster, much more energetically.
And that's burning. That's the heat we feel.
That's burning. That sudden release of motion energy is what we perceive as heat. And if the energy release is intense enough, fast enough, it can even generate light.
Flames.
Flames, exactly. Depending on how much oxygen is available, the carbon and oxygen might form carbon monoxide, CO1 carbon, 1 oxygen. Or, if there's plenty of oxygen, carbon dioxide, CO2, 1 carbon, 2 oxygens.
Oh.
And if we connect this to the bigger picture, these atomic rearrangements, this fundamental changing of partners, this is the basis for pretty much all the energy release processes we rely on.
Right.
From, burning fuel in our cars to how our own bodies get energy from food through cellular respiration.
It's fundamental, and it can get incredibly complex, too, like the example Feynman gives about the smell of violets.
Oh, yes, alpha iron.
Right. This specific complex smell is caused by just one type of molecule, alpha iron, which is this incredibly intricate arrangement of carbon, hydrogen, and oxygen atoms. And it just, accidentally jostles its way into our noses and triggers a nerve response. What's incredible is that chemists, through what Feynman calls these fantastic pieces of detective work, long before they could see atoms, they could figure out the exact arrangement of every single atom in these complicated molecules. They could even describe subtle details, like how a ring of 6 carbon atoms in alpha iron is puckered, meaning it's not just a flat hexagon, but it's actually bent or folded in 3D.
The specific conformation.
And that specific 3D shape is absolutely critical to how it smells or how it reacts chemically.
And what's truly remarkable, thinking historically, is the validation that came later. For maybe a couple of decades after chemists figured out these structures just through chemical reactions and logic, physicists started developing techniques like X-ray diffraction, which could physically probe the arrangement of atoms in crystals of these substances. And they found the chemists were almost always correct. Their deductions about the precise atomic arrangements, the bond angles, the 3D shapes, they were spot on. It's a fantastic example of how different branches of science, using totally different methods, converge on the same underlying reality. That collaboration, that independent confirmation, is key to building confidence in our understanding of this atomic world.
Okay, so bringing it all together, what does this all mean for us? How do we actually know atoms exist if, as we said, we can't really see them directly with an ordinary microscope or even an electron microscope in the way we normally think of seeing?
That's the crucial question, isn't it? The evidence.
Well, there are several really powerful lines of evidence that build on each other. First, maybe the most pervasive, is just the consistent success of predictions based on the atomic hypothesis. If we assume atoms exist and behave in the way Feynman described, attracting, repelling, moving, then our predictions about how materials should behave, how gases expand, how things melt, how reactions happen, they consistently come true. The model works.
It has immense explanatory and predictive power.
Exactly. Second, and this was historically huge, is Brownian motion.
The jiggling particles.
Right. Imagine you have a particle that's big enough to see under a really good microscope, but still quite small, like a tiny grain of pollen or a colloid particle suspended in water.
Okay.
Even if you can't see the water molecules themselves, if they are real and constantly moving chaotically, constantly bombarding this bigger visible particle from all sides.
The impacts won't perfectly cancel out all the time.
Precisely. There'll be moments where slightly more atoms hit it from one side than the other, purely by chance. So the visible particle gets jostled, it twitches and moves around erratically, randomly.
And you can see that happening.
You can see it. This perpetual, tiny, random jiggling of microscopic particles that was seen as direct, visible evidence of the unseen, ceaseless motion of the atoms bombarding them. It was incredibly strong proof.
A direct window, almost, into the atomic chaos.
Yeah. And finally, there are things like crystal structures. We mentioned X-ray analysis earlier. That technique allows physicists to map out the precise three-dimensional arrangement of atoms within a crystal. And what they find
perfectly matches the large-scale shapes we see.
Perfectly. The arrangement of atoms revealed by X-rays exactly explains the visible shapes and angles of natural crystals, like quartz or salt crystals, often down to incredibly precise angles, like seconds of arc. It's this beautiful alignment between the hidden microscopic structure and the visible macroscopic form.
So putting all that evidence together, the conclusion becomes pretty inescapable. And ultimately, the profound philosophical implication of all this is really what Feynman drives home. Everything is made of atoms. He even stated quite boldly that the most important hypothesis in all of biology is that everything that animals do, atoms do.
What does that mean exactly?
It means, well, in other words, there is nothing that living things do, thinking, moving, feeling, reproducing, that cannot, in principle, be understood from the point of view that they are simply made of atoms acting according to the known laws of physics.
So no special life force needed.
Not according to this hypothesis. It implies that life, in all its complexity, arises from the incredibly intricate organization and interaction of these non-living atoms. It's a statement that aims to unify all of science under this atomic foundation.
That is a truly powerful idea, isn't it? It makes you think. If just a pile of atoms arranged in a certain way makes steel or salt, and they have interesting properties, if water, just these little H2O blobs, mile after mile of them, can arrange themselves to form waves and foam and make the rushing noise of a stream, if all the complexity and activity in that stream can be nothing but atoms, then how much more is possible? If we as humans are, as Feynman puts it, just a great glob of these atoms in a very complex arrangement.
An incredibly complex arrangement.
An arrangement that's continually changing, never exactly repeating itself from moment to moment. The sheer potential complexity of what that arrangement can do, it just staggers the imagination.
It really does.
And there you have it, our deep dive into Feynman's foundational vision of atoms in motion. We went from the basic, relentless jiggling of these tiny particles,
The perpetual motion.
all the way to their profound role in explaining states of matter, chemical reactions, and maybe even the very essence of life itself. It shows how that one simple idea, atoms in motion, attracting and repelling, truly holds incredible explanatory power for, well, everything we see and experience.
It's such a powerful reminder, I think, that even the most incredibly complex things we observe can ultimately be broken down, understood in terms of these fundamental dynamic interactions at the atomic level.
Yeah.
And it also reminds us that our knowledge itself is always, an approximation. It's always evolving, always ripe for deeper discovery and maybe even correction down the line.
Indeed. Science is always moving forward. So let's leave you with this final thought from Feynman. If a pile of atoms, which is not repeated from one to the other, might have the possibilities which you see before you in the mirror, what incredible new possibilities might we unlock by continuing to explore the intricate, ever-changing, and utterly fascinating dance of these tiny, fundamental particles? Something to think about.